My friends, welcome to this week's weekend special. This is a series where I take a little complex model on the weekends and then try to solve them in FreeCAD. Today I'm using FreeCAD 0.22 developers version, which will be released. Rumors are that this will be the 1.0 version of FreeCAD. And today I'll be working on model Mania 2016. This is a model developed by SolidWorks. This is part of their yearly competition, and today I'll try to solve this in FreeCAD. With that, let's go ahead and see if the image can be used in the background to help us. It's almost calibrated there. I'll make it 50% and I'll probably keep it on XZ plane. Now it's on XY plane. I want to use this, which I will explain in a moment why I want to use that specific diagram. So looking at this hook or the contraption, the mechanical part, this middle diagram is actually gives the fact that this is a conical shape in the middle and a spherical shape on the top and bottom. None of these left and right side diagrams actually express that thought. So I'll be using this, and let's go ahead, relocate the image to help me use that diagram during sketching process. All right, so we are all ready to set doing the sketching. Now we answer the question, do we use part or part design? So I think I'll be using part design for this model, because there will be a lot of cutting things away, especially there is a hole with threads in there, and these are the strength of part design workbench. So I create a body, I create a sketch. I create the sketch on XZ plane, and then I take half of this object and try to make it suitable for a revolution, and that's what actually we are shooting for here, a revolution. All right, I'm using polyline, so pressing M on the keyboard actually helps. I want to bring it back and close the wire, and from my previous experience I know that this is a problematic automatic constraint, normal constraint, and I want to delete that right now. So and then make all these points coincident to each other. Now let's go ahead and apply some dimension, 44 millimeter, and this will be 20, the radius of this arc. So we don't have to do that since we already applied that 20 degree here, and this is going to be 14, and that constrains everything. Pretty easy. Now what I want to do, I want to take this sketch, actually rename that right now, base revolve, and do a revolution, and you can see the preview, and here that's what actually we want. The next phase, the next step is to build a hole right here, and I think I'll be doing that via a sketch on XZ plane, on this plane. And it will be a simple circle of 15 millimeter diameter. In part design, in part workbench, I would go ahead with a primitive and then make a cut. Now in part design, making pocket is easier through a sketch. Okay, so what I want to do is I want to select that sketch, it's in there, and hit pocket and see nothing shows up, and say through all, and now it shows up on the back, so we can say symmetric to the plane, and it shows up in the front as well. Pretty cool. The next phase is to do this hole that crosses here, but that one has a few ifs and buts in there. So let's take care of that. Because we will be doing this as a hole, in part design, pocket varies from the hole. A pocket is a hole, and a hole is a special hole. So that's how, I wish they named them differently, but so that's the shortcut it is. So this pocket would be specialized hole, and I will go ahead and change this image to YZ direction, and then do a sketch on a YZ plane, just a circle right there. So it will be just a circle, say 10 millimeter diameter. Now diameter doesn't matter because we can address that later on. So it doesn't matter as long as it is at the right center, which is 44 millimeter down from the origin. And that one, I'm gonna go ahead and say sketch bottom hole. So that's that hole is a technical term. All right, now look at this thread, which is the lower part of the nut of the bolt. And I think I don't know any specific trick to actually make it like in the lower part of the thread. I know that it can be done in the first half. So with that, let's go ahead and copy the sketch and paste it over, place it in there. So I have the same sketch twice. What I plan to do is, like, I will take one on the left and one on the right. So this one, the one that I just copied over, I'm gonna say this is for the hole, and I'm gonna say thread. So this is one with the thread, and this is one with this counter bore. So C bore. Okay. Now let's go ahead, take care of this thread part. So we have it in there, and maybe I want to switch it back to XZ plane, so that way it would be easier to actually decide which way to go. So I'm gonna go ahead and hide this and keep this one, and then make a hole. It's not okay, it's showing up on the right side. Yes, now there it is. And so the plan asks for M10. I'm gonna go ahead and say metric regular profile, and that's where M10 is there. And dimension, so it says 25. I know that halfway through is 20, so 25 it's okay, or we can say through all, either way. Maybe through all would do. Okay. And then type, so nothing, but we want to say threaded, right? And then I want to say model thread and update view. So it will take a second and show the thread in here. There. So we just got that. So we know that the thread is there, but I don't want to make it visible, because every time I do something changing, it will take a lot of computing power. I'm gonna go ahead and say model thread. I don't want to do that right now, but the thread is there. Just know that the thread is there. I'm just hiding it because I want to make it faster, the process. So we got that part done. I'm gonna say threaded bolt, right? And now let's go back to the counter boring. It will have to come from here. So I'll have to relocate this sketch right somewhere here. So 20 millimeter right side from where it is now. An easier way to do it, like, go to the attachment under the sketch in the data tab, and in the position. So now, not in the placement though, right? If it was in part workbench and then I'm moving some sketch or object, it would be in placement. But here in part design, the sketch moves from attachment, and on the Z, so there's a local distance is Z, and I want to move it on 20. So it may have a question in your mind, like, we are moving to X direction, why we are changing this Z value on the sketch? The technical answer is, this is global coordinate system, and this XYZ on the attachment is actually local coordinate system for the sketch. I wish it was global too, but let's roll with what it is now. Z will move it up and top and bottom. Okay, so we have that one located there. Now what I want to do, I want to select that sketch and make a hole, right? So it's getting inside there, pretty cool. Now on the profile side, we pick M10 again, and this time we are not saying threaded because it's not threaded. The plan doesn't ask for, so here it's not threaded on that side. Okay. Now one thing, we come here and say type, actually, okay, so it's going downward, so the distance it says 25. I want to make it 20, so that way it's not overlapping with that threaded part that we just built. And I will say counter bore, and the specification asks for 18.5 millimeter diameter, 5.5 millimeter down. So 18.5 millimeter diameter, 5.5 millimeter down. So we got that. Pretty cool. And I know that the drill point doesn't matter because we'll be cutting things away, but I want to make it flat here. All right, so that part is done. We got the holes as we needed. I'm going to go ahead and say C bore bolt. Okay, so up to this moment, both phase 1 and phase 2 are the same. After this point, what I'll be doing will be different for both phase 1 and phase 2. With that, let's go ahead with phase 1. I'm going to go ahead and save it. So I have the same object saved as phase 1 and phase 2. So when I'm done with phase 1, I'll just go to phase 2 and update this one, so I don't have to delete anything. All right, so let's work on phase 1. Here in phase 1, what it asks for is a rectangular block cut from the center and from two sides. So we can do that easily. So we'll just take care of this one first because it's the same XZ plane. And it will be sketch on XZ plane as I mentioned. And let's open up the section view. So this is going to be a rectangle, pure rectangle, right? And then this distance, okay, so because we don't have this pure distance from here to there, I can actually calculate it. So this is going to be 44 minus 18. Yes, so that's 26, and this gap is 15, and obviously these 2 points will be symmetric by the axis. The only thing left is this dimension, which is we can go as far as, you know, as long as it is past this point, we are fine. Okay, so this is the sketch bottom cut. Okay, and I want to make a pocket through all and symmetric to the plane. So that makes it a pocket through all to the symmetric to the plane. Okay, now let's go ahead, take care of this top cut. So we'll have to change the plane of the drawing, which will be YZ plane, and then we'll be cutting through here. So we'll probably have to move it there too. I think I can do it without moving it there. But for clarity of the operation, let's go ahead and actually move it. I think that will do. So what I want to do, I want to draw another sketch on YZ plane this time. Open up the section view. So I can take two rectangles right here and do it like that, but because in phase 2 I'll have to mirror it one part on the other side, I'll just do that from phase 1 as well. So I'm keeping this. The horizontal distance is 6, and the vertical distance is, we can go more than what we need, as far as we have this point fixed as 18. And then this distance, or again, we can go as far as I want, as long as it's cutting the whole thing. Okay, we got that. So let's put it in the body and make a pocket one more time through all, symmetric to the plane. So we got that. This operation, this operation that we just did, I want to mirror that whole operation on the other side. Select that part, come here with mirrored, right? So it's automatically picking this plane, which is good for me, and I'm going to say go ahead and okay. So that actually what does, it creates that block and then deletes it altogether, which is the strength of part design compared to part workbench. I think we're almost there. The one thing left is to do the filleting, and filleting is really easy on this one. Now, once we do the fillet, I don't think I'll be able to show the thread. So let me show you all if we have the thread inside there. So it's a threaded bolt. I come here and then from the data tab, I say model thread and say true. So it takes a minute and then shows the thread right there. So the thread is there. Just to reiterate, the thread is there. I just don't want to keep it showing, right? So we just turn it off. Now we focus on filleting. Now filleting on this model needs to be done sequentially, otherwise it may appear that filleting cannot be done. So I'm just taking these two inside part and these two, right? And then say filleting would be, the model asks for 2 millimeter fillets, and we got that. Now I want to take these two edges and these two edges, right? Maybe taking one of them would also work, but come here and then say another 2 millimeter fillets. All right, so that's essentially our model phase 1 built up to the spec 100% of what it asks. 2 millimeter fillet all around, and pretty cool. So this is the end of phase 1. Save it. And phase 2, as I mentioned, we will have to go back some distance and then update these cut profiles. Actually, we'll have to go back so up to this pocket 001, and that's why I actually saved it up, so we don't have anything after C bore. So after C bore here, we'll have to change everything for phase 2. So let's go to that phase 2 where we have this until here, and then let's see what phase 2 is asking for. Now phase 2 is asking for, where we did this cut with the rectangular profile, it is asking for a R22 spherical cut, right? So this is not even circular, this is a spherical cut. So we'll have to draw a curve in there and then make a revolve to cut it out. And on here, so this is only a simple cut. This is R20. So the inside one is spherical. This is only a curvature. So as you can see, this line is a curve, is an arc, and here this line is a straight horizontal line. So these are two different things. All right. So as usual, what I did in phase 1, I did this in lower cut first. We will do that one here now. So there will be a XZ plane sketch, and here I will be drawing an arc. Okay, let's open up the section view And then let's draw an arc something like this. All right, and this one will have a radius of 22. Cool. Now I want to make these two horizontal and then draw 3 lines to make it a closed wire. So that's essentially my sketch. Now all I have to do is fix them in plane. Now because I'll be doing revolve, I want to pull this up all the way up to here. So remember this distance was 44, and go ahead and make it 44. Okay, and this gap was 15, so that remains same, and this is already 22. I said it, and I just want to make sure that 22 is from this center. Yes, so this point will be on this line. There it is. We got that sketch easily, and now I want to do a group, right? So another naming convention thing, if anybody is listening, if this is loft, additive loft, and this is subtractive loft, this revolution would make more sense to have, say, additive revolution, subtractive revolution. Essentially that's what it is. I know group means subtractive revolution, something like that, but you get what I'm saying. So what I do is I select this sketch and click on the group, and we switch this sketch so it will be x-axis. We say x-axis, right? And that kind of makes it look weird, so maybe we'll have to go select reference actually. So I'll have to select this reference line inside there. Thank God there is a hole in here, otherwise we would have to go with section view. So we have this one, remember that's the one that we set at center, and that actually shows a nice cut, and we are happy with that. So that's our first cut, but this is spherical. This is a curved surface, and also the whole thing is a curved surface. It's like two-dimensional, like two-directional curve sphere essentially. Okay, let's do this top one. It would be simple as well. So we do another sketch on YZ plane, and then so this time it will be simple as rectangle, the same rectangle, but it will be from this axis. So the distance is 6 if I remember correctly, and this length would be, let me take a look, this length is 20. Okay, so I have to click first and then say 20. Okay, so that's a pretty close gap right there, very close, cutting pretty close. All right, and this length, as long as it's cutting outside, so say 12. Cool. Now what I do, I take this one and do another group, pick y-axis. Okay, so this little tiny thing helps all the time. All right, so we see a nice cut. Cool. I take this group and do a mirror on this side and hit OK. So that's our phase 2. Now how we cut it makes the difference. Okay, let's see if we can do the filleting. So we select these 2 lines, right, and these 2, and then say fillet 2 millimeters. Cool. Now I take any of these edges, 2 of them, and maybe take only one of this, it will actually come around, and then say 2 millimeters. Pretty cool. It does look like our model. Phase 2 done successfully. So this is what the phase 2 looks like. It has these threads, and we established that the threads are there. I just don't want my computer to hang up on me, so but the threads are there. And also, now that we did some filleting, I'm afraid to show those threads. That way it may mess up the fillet. Alright, if you need the thread showing there, I would recommend you do that, you make it visible before doing the filleting, because filleting is actually, it depends on the edge name. All right, so the modeling part is done. This model also asks for an FEM analysis. It says use, okay, what does it say? 5000 loads in here and 2000, and fix these two centers, and then see material. It must use some material. Okay, it has plain carbon steel, and that's it. Okay, so let's go to FEM workbench and start a container which will have a solver inside there. If it doesn't have, add a solver from here and add material. So it says plain carbon steel. I don't think it has any plain carbon steel in here as plain carbon steel, so I'm gonna go with, say, steel 1C35. Right, and if you didn't know, we can go into this FreeCAD material editor and look at the ultimate strength and yield strength of this material, which is 300 MPa for this. And then let's go ahead and fix these two edges, so this one and this one. Now that we don't have any threads, it's easier to actually select, so I would not recommend you keep those threads showing during this FEM analysis. Not recommended. I have never tried it, but I don't recommend it either. All right, loading. So we come to here and it says add. I want to add this surface. I want to make it go upward, so we'll have to find an edge that goes upward, which you don't have. Okay, I had this problem in one of other videos, but I didn't have any vertical edge to select. So what I did, oh, here is one. No, that's not vertical. Okay, that's an issue. Let's go to the origin and make the z-axis. Can we make it visible? It's not. So none of these are visible. Oh, we can make the origin visible. All right, and now select load, add this face and select one of these edges. So z-axis, I selected it. Okay, let me take this add off, select this z-axis and say direction. I wish somewhere here in the direction this standard 3xyz options would be there, so I don't have to fetch it from somewhere else. But so there is 5000 Newton load in this upward direction. We got that, so that's added. Let me go ahead and hide this origin. Okay, so load is done, and now we have to add this mesh. So we can add the whole mesh or the fillet. So I'm gonna go ahead and select the fillet, add gmesh. I'm gonna say first order and keep it automatic. Hit apply, see how it plays out. It played out good. So we are looking at 6 point, this end value gmesh done in black. no red. Okay, we have everything. Now we can go to solver, double click on it and write the INP file and hit calculate and keep your fingers crossed. All right, it didn't take long, only 7.6 seconds, and we have our object. All right, so what are we looking at out of this FEM analysis? We did the analysis, and what does it mean? We can take a look at it. So let me hide this mesh and hide this result. Okay, let me take a look at this CCX result. So double click on it, and now we can look at two specific things: displacement and stress. Okay, maybe I want to hide this original body as well, and go to CCX results. And now, so displacement wise, we can see that the displacement is really small, 4.61 micrometer. So that's like 0.004 millimeter. So we can take a look at it. It's magnified by 10, and we can say show it, and it will, yeah, no, it doesn't show that much. It's like, so we'll have to make it really big. So now we can see it's moving upward, but mostly this part, none of this portion is having any deflection because of the how the materials is distributed. This is the thinnest part and this is the thickest part. So the thick part doesn't have any, normally any deformation. The deformation comes in the thinnest part first. And we also can take a look at the stress. It says that 27 MPa is developed stress, and maximum stress is being developed at somewhere here and in here. So remember, when we were looking at this property of this material, the yield stress was 300 MPa. Now the developed stress is 27 MPa, say 30 MPa. So the factor of safety is like 10, which means we can apply more load. So we can make this even 10 more times. So 50, we can make it 50 kilonewton, and then do the analysis one more time, right? And it was even faster this time. And let's go to the CCX results and see, this time it has, so 10 times the load. We are still not failing. We are still, this material is safe to still safe to use. So 273 MPa, which is less than 300 MPa, I'm going to say factor of safety is more than 1, so it's not failing. The magnitude of displacement, however, will be increased, so that could be another limiting factor in the field where we don't want this much of a displacement. So that could be another things to look at. So stress is not the only limiting factor. Sometimes the displacement becomes an issue as well. All right, so this is the FEM analysis, and we looked at the results and see how those results are interpreted, or like, you know, how what it means. And I think that's the end of the video. I hope you enjoyed the model building in both phase 1 and phase 2, and also doing the FEM analysis and how those results are interpreted for this model. If you have any question, comment, or suggestion on this model, please let me know in the comment section below. Thank you for watching. I'll see you in the next one.